Hello everybody and welcome to the NPTEL online certification course on microelectronics devices circuit. What we will start today's lecture by just recapitulating what we did in the previous turn. We had seen that given a NPN transistor where emitter is basically an N type, base is P type and collector is again N type, base width is very small, emitter doping concentration is the highest, base doping concentration is the lowest and collector is moderately doped. We have also seen the reason why the base is relatively lower doped, and the reason was that with low doping we will have less number of majority carriers there, and therefore the electron hole pair recombination there will be smaller, and as a result most of the electrons which started from the emitter side will reach toward the collector side and you will get a large current on the collector side. So, that was the primary reason why the base width was effectively very thin, and not only that, the base doping concentration was also very small. With these two things in mind, we have also seen yesterday in the previous discussion or in the previous lecture that the base current itself consists of two components. The first component is primarily the current which is the base current which is coming out because of the recombination of holes. So, when electrons recombine with holes, to replenish those holes you have to insert a current, that is one part of the current, which is basically a current which is being supplied by the forward bias base to emitter junction. There is also a current which is basically a current which is primarily due to the diffusion of the minority current carriers, in this case electrons from hole to the base side to the emitter side, because that is, though it is forward bias, but for that it can easily move through the region. Now we have also seen in the previous turn that with this basic concept there are two types of transistors available, what is known as NPN and you have also a PNP transistor. We have also seen the various modes of operation and how the various modes of operation work, under what condition. For amplification purposes, as we have learned, your emitter base junction should always be forward biased and your base collector should be reversed biased. Similarly, if you want to do it in a cutoff mode, then both the junctions emitter base and collector base should be reversed biased. If you want to move into saturation, then emitter base should be forward biased and base collector should also be forward biased, and so on and so forth. So, we did have two biases and two types of combinations. So, there were effectively 4 modes of operation of BJT which we have dealt with in the previous turn. We have also seen that in the previous turn that if you have a therefore NPN transistor, right, and then if you want to plot the minority current carrier concentration in the base region, then it was shown to you that in the base region if I plot a graph, then in the base region I would expect to see the minority current carrier concentration to fall almost linearly, right, and this linear falling is primarily due to, so this is basically a linear drop in minority concentration, right, and this is minority concentration. This is primarily to do with the thought that your doping was low and your width of the depletion region is also low. Under these two criteria we saw that it is almost like a straight line, which is falling between point, and as you can see on the so this is emitter base collector, this is basically your EB junction, emitter base junction. Your concentration of minority current carrier is maximum here, right, and it becomes linearly to become almost minimum at this point. We have seen why this profiling is being maintained to a larger extent. As you can see, this will be primarily a diffusion phenomena, right, and therefore will depend upon the concentration gradient of the charged particles, which is basically here electrons within the base region. Today what we will be looking into is have a look into our basic fundamental principles where we left yesterday. If you look very carefully, then the minority carrier concentration will be proportional to e to the power or exponential VBE base to emitter voltage and divided by the thermal equivalent voltage, which is effectively equals to 26 millivolts. So, Vt is equals to 26 millivolts at 300 Kelvin, right. Vt equals to 26 millivolts at 300 Kelvin, which means that as VBE increases, base to emitter voltage increases, the value of NP0 is it should not be NP0, it is basically the formula is NPx at any point is equals to NP0 e to the power or exponential VBE by Vt. Please make a correction here that it is Npx will be equals to Np0 exponential VBE. Now, what does it tell me about this this thing? So, if it is Npx equals to Npx is the distance from the base region, Np0 exponential VBE minus by Vt. As you can see from this concept or this basic idea, Np means N suffix p means this is basically a minority carrier concentration at p type. So, it is for at p type base at x equals to 0. So, x equals to 0 primarily means if you look at x equals to 0, it basically means this point, this corresponds to x equals to 0. And let us see if we proceed forward, it gives me an exponentially falling drop, which means that though it is basically shown as exponential, we approximate it as a linear fall in concentration of electron, as you can see. Therefore, if my VBE would have been larger, this is where the basic fundamental principles comes. If VBE would have been larger, I would have expected to see the value of Npx to be also large, right. Is it okay? For the same value of x which you see. So, because if VBE is typically large, then I would expect to see Npx to be also large, because it depends upon the value of any particular point. Now, the point which I wanted to make overall expression therefore is that if, so therefore we define in this manner. Now, the electron now so you see, so therefore what will happen is for the minority current carrier, it will be basically a diffusion current which will be flowing in the base region from a region of high concentration on the emitter base junction to a region of low concentration or almost 0 concentration on the base collector junction. Now, will obviously this current will depend upon the difference of the concentration at the interface between emitter base and base collector. So, as you can see here, the electron diffusion current In is directly proportional to the slope of the straight line of the concentration profile, which means that if concentration profile is assumed to be straight, I can very well find the value of current In to be equals to AE multiplied by Q multiplied by Dn multiplied by dNpx dx, right. This is a standard formula for finding out the current, where AE is the cross sectional area of the base emitter junction, right, is the cross sectional area of the base emitter junction, Q is the electronic charge, D is the electron diffusivity in the base, and W is the effective width of the base, right, and W is the effective width of the base. So, you see In, therefore, if you take this equation, right, and then this comes out to be minus Np of 0 by W, and the reason being very simple, because we have assumed till now that the fall in concentration or the drop in the concentration will be almost a linear drop, right. We have already assumed that it will be a linear drop. So, if it is a linear drop, then it is very easy to find the slope of a linear graph, provided you know this is basically your Np0, which means the concentration of minority current carrier at the edge of the emitter base junction. So, this is my emitter base junction and this is my my collector base junction, right. This is EBJ and this is my CBJ. Then this minus 0, assuming that you have reached the 0 value, I get Np0, and this is basically your W, width of the base region, right, and that will give you the value of In in this case. Please understand one more important point here, that in no way, right, the depletion width on the emitter base or the collector base junction is influencing your electron concentration in the region of the base, minority current carrier contribution, because they will be nonetheless available at those particular points, and therefore, it will not affect the overall concentration of the minority profile in this case, right. So, this is what we have learned, and so we have learned this basic fundamental principle, that therefore, current will depend upon the area AE of the emitter, and it also depend upon the minority current carrier concentration of the emitter base junction, right. And we have assumed at this stage that the minority current carrier concentration on the collector base junction is approximately equals to 0. If it has got some finite value, obviously this will be a lower, this will be a lowered value, and therefore, I would get a lower current, right. So, higher the difference or higher the gradient between emitter base and collector base in terms of concentration gradient, I would expect to see a larger current to flow in this region, right. So, we have learned therefore 2 or 3 important points out of all these discussion, and the first important point is that the diffusion current is independent obviously of the applied bias. It only depends upon the area, the diffusion constant, and most importantly on the concentration gradient, which you can see from this equation in front of you, this equation, right. With this knowledge or with this idea, we come to the next idea, which is basically my collector current. Now, assuming that you did have all the emitter charge carriers which were electrons, and there was 0 recombination in the base, I would expect to see all the electronic charge reach the collector side, right. So, I can safely assume in that case that my electron current IN will be equals to the collector current, right. So, contribution in the whole is relatively small because it is a minority current carrier, and therefore, the major contribution is from the majority current carrier, which is basically the electrons, and therefore, I safely write down IC to be equals to IN, right, and that is known as the basic equation which you see. Now, IC, the collector current, can be written as IS e to the power VBE by VT. So, IC equals to IS exponential VBE VT, right, where VB is the base to emitter voltage and VT is the thermal equivalent voltage. IS is defined as the saturation current, right, very small current, but it is a saturation current. Now, so I get IS, therefore, what we can write down IS to be equals to this much. IS is the saturation current, AE into dN into Q into NP0 by W, right. If you look in the previous slide, you see you have a negative sign here, right. It is a negative sign which you see, and the reason is that the concentration starts to fall down as you move from x equals to 0 to x equals to W. So, there is a decrement in the concentration, and as a result it is a negative value which has been shown here. Now, as you can see here, IS is given by this formula because I just replaced IS by AE dNQ NP0 by W, again assuming 0 charge carriers on the collector base junction. Now, from my earlier basic semiconductor physics theory, I get NP0 to be equals to Ni square by Na, right, where Ni is the intrinsic carrier concentration and Na is basically my acceptor ion concentration. And therefore, if you take NP0 and place it in this equation, right, I get IS to be equals to AEQ, IS to be equals to, right, AE multiplied by Q multiplied by dN multiplied by Ni square divided by Na into W. W is the width of the base region, which means that that IS, the saturation current, depends on the number of intrinsic carriers, which actually doubles for every 5 to 10 degree rise in temperature, right. So, you would expect to see a very large change in the value of saturation current in this case. Second important point which you should be very careful, and you can go through it, you can see it, is that as the area of the emitter, the cross sectional area of the emitter increases, your short circuit, your IS also increases. So, IS is therefore is directly proportional to AE, right, and IS is also directly proportional to Ni square. Since Ni is directly dependent on as is a function of temperature, I can safely assume that IS is therefore also a function of temperature, right. Higher the temperature, higher is the value of IS, which is the saturation current in a standard NPN or a PNP transistor, right. Now, my base current therefore IB is equals to IC by beta, and therefore, we define beta to be as a common emitter current gain, because if you look at beta, beta is basically IC by IB, right, under the condition that you have a common emitter configuration. So, it is basically output by input, and therefore, this is also referred to as a current gain equation, right. Therefore, again as I discussed with you just now, IB will be equals to IS by beta into the e to the power VT by VT, right. Typically, current modern NPN transistors have beta in the range of 550 to 200, right. The typical range of beta is between is typically between 50 and 200, right, and this range depends upon many factors. Apart from the material of the device, it also depends upon the type of doping has been done on the device, the level of doping which has been done on the device, right. Now, if beta is high, beta is basically, as you can see, is basically IC by IB, right. So, if beta is typically of the order of 500, 200, 300, so on and so forth, it primarily means that your collector currents is orders, maybe 2 orders or 3 orders higher than the base current, and this is expected also. And the reason behind this is that all the carrier concentration which was available to you from the emitter side, right, goes towards the collector side, right, and therefore, recombination of electrons or holes on the base region is very minimally low. When it is low, your beta value actually becomes typically large, because your IB value reduces drastically, right. So, as you can see, beta is highly influenced by the base width and relative doping of the base region and emitter region, right. So, it depends upon Na upon Nd, right. I suppose you will be able to find out why and how, right. I will leave as an exercise to you to please understand why is it like that why beta, it depends upon the base width region of the base. If it is very thick, then beta is relatively small. If it is very thin, beta is relatively large, and so on and so forth, right. I leave as an exercise to you to find out the value. Kirchhoff's law cannot be violated, all of us know that. Over the years we have seen that it cannot be violated in more sense than another, and therefore, I can write down IE to be equals to IC plus IB, right. If you go back to your previous slides as far as this course is concerned, then you will see that, or maybe let me draw for you that if I have got a NPN or a PNP, right. If I have an NPN and a PNP, then what I get from here is that this is forward biased and this is reversed biased and this is forward biased, right, and this is the width region, with W is the width of the of the base region, which is opposite lead biased as NNP region. Now, if you look carefully, the total, so it is an NPN. So, if its an emitter current is IE, this will be IB, and this will be IC. So, I can safely write down IE to be equals to IB plus IC, and this is basically charge conservation principle. So, this is basically a charge conservation principle, that the charge is always conserved irrespective of the type of device you take, or the irrespective of the type material of the device you take. So, IE equals to IC plus IB, because you will be following the Kirchhoff's law, and since you will be following the Kirchhoff's law, the total emitter current which is entering into the system must be exactly equals to the total so if you look at very carefully, I equals to IB plus IC, and therefore, total emitter current in the system is sum of base current and collector current, right, and that is how you manipulate. So, you try to therefore maybe control the flow of the collector current by increasing or decreasing the value of the base current, right. By changing the value of base current, you can actually make IC or IE almost close to each other, right, and that is a major study area which people are working. So, IC plus beta, we know that IE equals to beta plus 1 upon beta into IC, well that is a standard formula which people use, right, and then IE will be therefore equals to beta plus 1 by beta into IS e to the power VB by VT, and from here I get IC equals to alpha times IE. So, all this IC part which is basically your this part, right, is IC, right. I get IC to be equals to therefore alpha times IE, which is a known fact, alpha therefore is equals to IC by IE, right. So, and alpha is therefore referred to as common emitter current gain. So, alpha is known as common base current gain, beta is a common emitter current gain, and as you can see alpha depends upon the value of IC and IE, which is understandably so, because IE is basically the total current being entered into the system and IC is the total current exiting the system. So, if you solve it, I get IC equals to alpha times IE, right, I get IC to be equals to alpha times IE, right, which means that and this is quite simple and straightforward. So, alpha will be very close to 1, if it is 1 then IC will be equals to IE. In that case we are assuming that all the charge carriers which were initially originating from the electron or from the emitter side will actually terminate on the collector side, and therefore IC is written as alpha times IE, right. Two important equations to take care of, alpha equals to beta upon beta plus 1 and beta equals to alpha upon 1 minus alpha. These two important equations are required for solving problems, right, and that is quite interesting problem solving which you can do using these two equations, right. Let me come to the last part of our talk, and that is basically your large signal equivalent circuit model for NP and BJT. Well, you see what we try to do is that when we have a device primarily in its initial stages of fabrication and testing, we want to convert that device into an appropriate machine or a simple machine, so that we can actually record its current versus voltage characteristics in a much better manner, right, and therefore we need to do a circuit level implementation of the device. So, this is basically a large signal equivalent circuit model of an NP and BJT, which means that if you take a BJT, right, and place it in a large circuit domain, then we can replace that BJT by these large signal equivalents, right, these large signal equivalents, this one as well as this one, right. You cannot do this or this, but these you can surely present as an amplifier. Now, let us see what is what. As you can see, base current is the emitter current, right, and base is the test terminal, IC is the collector current, and C is the collector profile, and E is the emitter terminal, and IE is the emitter profile or emitter voltage or current which is available in here. Now, you see if you look very carefully that whatever voltage source was there on the source side, right, we were able to give that voltage source and draw a current. This current was same into the collector current. So, collector current is approximately same as the base current, the emitter current. The only problem is if the base width is large or the doping is relatively high, then this assumption does not hold good, right. As long as the base width is small and your dimensions are or your values are very small in terms of potential, you will not be able to do this problem in a proper fashion. You see here, if you look at the first picture or the first diagram here, the schematic here, you will see that I have replaced the collected side by current source, right, and that is true also. If you look very carefully, once if you plot VBE versus maybe if I plot VBE, right, versus IC collector current, right, and most of the time it will be difficult for him or her to explain to me this IC versus VBE of any typical bipolar technology which you see. If that is the case, we assume that the base side potential is always fixed, does not vary, and therefore he is not it does not vary to a larger extent, and therefore the collector starts to behave like a constant current source, which means that even if you change the reverse bias of the collector base junction too much, the current does not change too much. So, as I discussed in your previous turn, it starts to behave like an ideal current source, right. So, if you plot IC versus VCB, I will almost get like something like this, a constant current source, right, which means that I can replace the collected side by a constant current source. If it is ideal constant current source, my output impedance will be infinitely large, right, and I will get almost fixed value of current even if I change the value of VCB too much, right. And therefore, you see this part, which is the collector part, is basically a controlled current source, right. So, it is basically controlled current source. Who is controlling it? The value of VBE, base to emitter current, right, that is controlling the collector current. We have already discussed this point, and VT is a thermal equivalent voltage, right. So, let me recapitulate what we have learned till now. We have presented a first order equivalent NPN model operating in active mode. Active mode is when emitter base junction is forward biased and collector base junction is reverse biased. Any forward biased profile or a entity will always cause an exponential change in the value of current, right, and therefore, the collector current IC is independent of the value of the collector voltage as long as the collector base junction remains reverse bias. So, as long as it is reverse bias, I do not worry what is happening on the other side. On the other side means on the side of the collector, and we end up having therefore almost a steep profile in this thing. In active mode, the collector current terminal behaves like a ideal current source, we discussed Y, and the base current IV is a factor of 1 by beta of IC. So, basically 1 by beta of IC is equals to 1 by IE, right, or 1 by B, right. So, I can safely write down beta to be equals to IC by IB, but IB is the base current, right. It will be a very small quantity, but nonetheless the base current will be there, which is available to you, right. So, this takes care of all your discussion here. I thank you all for your patient hearing. Thank you very much.